Okay, so let's give it a minute or two to percolate through, okay? Just because this was on the announcement, I think that it's probably the folks out in the hinterlands have probably seen it. Believe it or not, still to this day, they are selling vacuum tubes, and this isn't a new thing. The tube store, it's just a remarkable thing to me that you can still go out and get a 6L6. In fact, not just any 6L6, several different kinds. And bizarre as it may seem, they're not all from Soviet land, former Soviet land. They're not all from China. I mean, I'm not sure where Siemens makes their tubes these days, but
for those of us ignorant of vacuum tubes, what is a 6L6?
6L6 is probably the most common audio amplifier last stage tube. This is the one that would drive right into the transformer, the output transformer, and a big innovation after that, years after that, was OTL, output transformerless audio amplifiers. But you know, still popular in the stages, the heavy duty current carrying stages of guitar amplifiers and things of that sort. So it amused me. I was interested to see it. Now, in the olden days, apparently, line voltage was lower. So you plug your antique Fender Deluxe amplifier in to the modern line voltage wall plug, and it puts out too much juice. This causes damage. So this is a solid state replacement for a particular rectifier tube used in the Fender Deluxe amplifier, and it does two things. One is it does the function of the original device, and two is it's gentler on the other tubes and the filter caps and things of that ilk. So, you know, this 6V6 GT tube, well, thank you. Has anybody seen Banggood out in the world?
Never seen one, but they look interesting.
Yeah, this company has more stuff than you would believe possible from one vendor of all this bizarre, diverse kind. Banggood. You get more bang for your buck, apparently, from Banggood, and it's good bang, apparently. You plug it into your USB spigot, and it tells you what else you plug in, and it's current draw. So if you've got two items, let's say you've got a laptop and a cell phone that you're charging from it, and you plug it in and something goofy is going on, it's not charging or something, you can plug this thing in and it'll measure the voltage at the USB port and the current. And that's pretty cool. And you can try and diagnose voltage and current related issues. So I announced this exciting activity of looking at new things. Does anyone have a link or a thing that they would like to tell us about? Good. Heck with you. I've got a list.
I sent you over.
Yes. We'll get to it. Not
entirely fork related, but months ago, or anyway, weeks ago, the government of France, I think, said it's not enough that Google delete things that people who are embarrassed would have private. So take it out of you. But that this becomes newsworthy, you must not index those news articles. It's okay if you talk about them in the news, but we don't want years later folks digging up salacious news just to get the goods. So Google now, except they say no, except now some Euro judge says, oh yes, you will, except there is an appeal, but it is Europe. And the idea being that if you do something naughty, it's between you and the state. And your neighbor has no standing. The right to be forgotten, yes, the right to be forgotten.
Yes, I think that that would interfere with Megan's law in this country.
Unaccountability law. To be held unaccountable, to be not held accountable.
All right, this is something that, this bus pirate is something that James talked about this morning. And that was kind of cool.
That's really cool. Yeah.
Yeah.
Very cool. Because I squared C, SPI, good.
No, he cut out the
He
thing.
showed the I was curious about the FTDI one that he had, but
4232? Is that what it was? Well, the 4232 is 4 modules actually to do like 4 UARTs, S5, X2C, and GPI.
So there's an app for that, apparently. It's not enough that you be able to plug it into your phone. This one's apparently Bluetooth. We're getting to that. In fact, let's get to that next, because licensed beverage of thinkgeek.com, apparently. Where's Sam? Can you attest to this validity of this particular product? All right. Sam's a good sport. He lets me taunt him. All right. So give me a hint. Refresh my memory, Dennis.
what?
I meant to flag your particular contribution. Do you remember what your
I have it here in a moment.
okay. While you do that, I'll move on.
Spark Fun.
Oh, yeah.
Photon kit.
Oh, okay. There are 2 of these sort of steampunk thumb drive deals. This one looked kind of cool to me. When I saw the photon kit, I thought that this was some kind of April Fool's Day parody. All right, I shall. But apparently you're not making photons. You're using a processor that has particular application to the Internet of Things. Anything else I should say about this?
Nope. It's just a, I'm noticing more and more of these export restricted thingies.
Export restricted, you said, Tess.
In your thing. Mine also, it was export restricted.
Yes. And it just goes to show you. Yeah. Well, I guess there was a T-shirt one time that had some, what was it, pearl code on it that was a munition under the. All right. So this is the USB pet rock. Because I'm easily amused. Yeah. So, yes, it does everything the pet rock does.
For people interested in FPGA computers,
Okay, let me see if I can bring that up.
go to Terrasic's website. It's really easy to find. Just TE. We go, yeah, Terrasic DE2, RD1. Yeah. There you go. That link right
Yeah, all right.
there. But people want to make their own fourth computer. This has all the peripherals you can use.
I'm told that if people want to make their own fourth computer, this has all the peripherals one might want. Thank you, Todd.
Slide switches.
How much was it? This is cool. I wish I'd had one of these when I was a young miscreant.
So you can get a feel for picking a lock.
Well, I once tried to explain how pin tumblers locks work without drawings or illustrations, and it was difficult. So here's your fuel cell to charge your cell phone. Years from now, you know, the bright young kids will ask each other, well, why do they call it a cell phone anyway? And the smart kid will say, well, because it runs off a fuel cell, silly. And it'll just be sucking water out of the air and hydrolyzing it and using the energy from the hydrogen. Sure. So this is the flag of Nepal. As far as I can recall, it's the only one that isn't a rectangle. And oh, by the way, this is our challenge for all of you fourth haiku folks to reproduce this. If you didn't listen to Brad's talk, you're going to have to go back to it later. But for now, start work. Okay.
There are a bunch of others there that aren't rectangles.
Oh, okay. John says that there are a bunch of others that aren't rectangles. That's not a country, though.
They would like to be.
And for people doing remedial haikus, particularly surrender flag.
Okay. David suggests that you do the surrender flag for your haiku fourth challenge.
Train the flag on your browser.
Oh, that's pretty good. They're watching channel.
Just do control minus.
Yeah, it's $1 a watt, apparently.
It could be very inefficient.
It could be very inefficient. Yeah. I deal with it.
So every once in a while, I need some kind of weird tool.
Well,
And this is the folks at iFixit, and I recommend them to you for purposes of all their cool tools and all of their bits that fit all of these weird screwdriver screws that you can't get drivers for elsewise. And did I mention that their teardowns are really, really cool? And Sam will be moseying on up in a couple of minutes. Anybody know the answer? Word boycott entered?
Farming protest.
You're right. Thank you. Azerbaijan spas. We'll come back to that one. So I saw this picture. This is not new either. I saw this picture of an expensive watch, and I clicked on it, and it turned out to be a shopping website that you had to log into. And then the next thing that happened is I said, well, I'm not going to give them my email address or anything. So I did a Google image search. And how many of you realize that you could give Google a picture and say, find other pictures out on the web that look like this? Did anybody not know this besides me? Okay. So this is a cool thing. You can send a picture to Google and it will find other pictures on the web that look like this. And I found another site that had the same really freaking expensive watch. And that was the point of that. And it didn't come up properly. So we moved on to the next thing. This is another thing from Banggood. This is a key machine so sophisticated that there are locksmiths that don't have the effective equivalent capability because they just don't feel it's practical to make these goofy kinds of keys that this thing can make. And if I may say so, it's reasonably priced. All right.
Go back to one, also 220.
Go back one.
Just go back one page. You had something that said a high-speed book scanner.
Oh, yeah. Okay, sure.
Down BFS down, it's like third from the bottom. It's like, there we go.
I was kind of hoping that I wouldn't get.
Once, right?
It's pretty cool in that it puts down a mapping laser pattern. It analyzes the shape of what it's seeing, and in software, it flattens the frickin' page out.
Cool.
And it does it all frickin' fast. And this, note this.
They have a video?
That's a video. Dude, that's a video.
But first, I wanted to get out my lightsaber and point at this. 250 pages a minute.
I want to see it.
It's like magic.
Yeah, I want to see it.
Just because you see it, that doesn't mean it's real.
The entire theory of our system of government, the United States, Canada, the British system of government, the entire theory.
That's another video that appears to be running simultaneously. No, that's Bill Whittle blathering about some damn thing. So those of you at home, you're not missing anything. There's no sound to this video. Someday we'll find a way to get the sound to you for all these videos.
But still, that was Chinese. I mean,
That's impressive.
that's real impressive.
The reason I asked about this was my uncle had invented a page shirt back in the 70s.
Everybody's got that.
And you were able to have like a 500-page book.
Oh, that's hard.
Huh?
That's hard.
That is very helpful. That's also involved. They use electronics.
It's something that's needed by people who don't have.
Yes, exactly.
That's you got?
No.
What was the price on that, Kevin?
I guess that's outside the scope of my presentation. There wasn't any price information available to me. So this is the really expensive watch. It's a good example of if you have to ask, you can't afford it. So this is the most recent example of a driver that you can't get in the world that they have at iFixit. Is this JIS, Japan Industrial Standard. It's like a Philips, only just different enough to be different. So there are two sites I'd like to show you. This is the worst things for sale on the internet. And it is a bunch of pictures and descriptions of products that you wouldn't really want to buy.
That's just disgusting.
I don't have anything against George Takei. I'm just suspicious of any product where the makers clearly thought of the name before designing the product itself. So there's also another site that I'd now like to point out. This site is called This Is Why I'm Broke. And they've got a lot of interesting products available on the internet, like this water dirt bike, this black water. I'm not sure what that's about. This Game Boy refrigerator magnet, so you can put refrigerator magnets on your refrigerator to make it look like a Game Boy, or for that matter on your washing machine. And the reason I'm showing you these two websites together is that it's remarkable to me how much overlap there is for these products represented on both of these websites. Certainly with different context, but now Sam will start moseying forward while I continue my blather, and we'll do a smooth handoff in scant moments when he's ready to start his. Now, here's an interesting one. This is the Everything You Need to Fix Stuff toolkit from iFixit. And the reason we wound up looking at it is because it was in the list and it said untitled, and I couldn't resist. This is a product called Tile. And they're these little things you stick on stuff, and I guess it uses low energy Bluetooth to talk to any phone that's in the neighborhood. And if this product doesn't do that, there's another product that does. Anyway, you pay a subscription, and your keys or your cell phone or your whatever comes up on a map on your phone, your bicycle perhaps, whatever it is you're going to lose. And it comes up on a map on your cell phone, and you can make it ring. And with that, I'm going to hand over the video spigot of doom and commend you to the tender mercies of the next speaker. Man who needs no introduction.
And I am merciless. And hopefully I don't hit any. Hang on, I'm getting there. I just hope that I don't hit the mute button. And wherefore is video blue? Yeah. All right. So we have that. No, I have a background that rotates. All right. I kind of wish that my screen was share. Come on, you. Wow, really?
Well, who's doing that? I have a picture here. It looks like you might expect. You can see it at the break. Years ago, I had a thing called, I can't remember the name. Mattel made it with cooperation from Intel. It was a microscope for kids that had a USB port. Unfortunately, I think the software is no longer compatible with any computer made in the last 5 or 10 years. Anyway, if you go to Banggood, they have a USB 8 LED 50 to 500x 2 megapixel digital microscope, endoscope, magnifier, and video camera. That endoscope thing makes me a little nervous. $14 a pop, US. Free shipping. No kidding.
That's a deal, man.
Well, maybe, maybe not. I guess you have to buy one to know.
Yeah,
And with that, it looks like Sam is ready to shoot.
I am. I'm. So my goal of getting my screens to share has failed miserably, but that's okay. There we go. Keyboard is working. Okay, so my name is Sam Falvo, and as usual, I'm giving an update on the Kestrel 3. A fairly in-depth topic today. I fully expect people to probably fall asleep. I won't be offended. Thankfully, this presentation is going to be streamed online, so people can refer to it later. This is probably the longest slide deck I've ever done in my life. It is over 70 slides. All right, so disclaimer. Oh, yes, I'm talking about patient I/O, as in case you hadn't noticed. Disclaimer, though, this talk is entirely speculative because I still don't have any hardware. I was hoping to have something done by now, but you know, that whole work-life balance imbalance thing, I think we should just stop calling it work-life balance. And well, marriage is okay. It's the work-life imbalance. So yeah, I reserve the right to change anything at any time for any reason whatsoever. So basically, I'm, as you saw in the title of the slide, how I think the Kestrel 3 will use rapid I/O, that basically means that I can decide at any time that I may not want to use rapid I/O. But honestly, I think I will. So it's divided up into 6 major parts. They kind of build on each other a little bit. Well, at least the first 3 parts do. And then in the middle, we've got the keyboard, mouse, and network adapter. This is the how I think the Kestrel will use this technology bit. And then I will go super speculative in part 4, part 2, which is someday patient I/O in pure hardware. That should be part 6, but I just finished the slide deck not 15 minutes ago. So, okay, so why do I need any kind of intelligent I/O at all to begin with? Why can't I just bit bang things like I did with the Kestrel 2? Well, it happens to be the fact that my coworker at Rackspace, his name is Ken, challenged me to use the Kestrel 3 at work, for a duration of 5 days. What this basically means is I need to do all of my Python, JavaScript, Ruby, and various other software development for Rackspace in particular on the Kestrel. And this would actually be an interesting way to dog food the computer, in fact. So I accepted the challenge. But it's a little bit impractical to port all these development tools in relatively short order, so especially doing it myself. So basically what I'm planning on doing is just the absolute bare minimum to actually meet his criteria for success. And what I'm going to do is I'm going to use virtual network computing protocols, the remote frame buffer protocol, as a means of giving myself a graphical interface. It will actually be talking to a Linux cloud server in the background. And originally, this was intended to go over SSH as well to secure the link. But then I looked at the SSH protocols and I realized, no, I don't have the time or patience to implement anything even remotely as complicated as SSH. So I will instead go from the Kestrel 3 to my work laptop over a local wire, an actual physical wired Ethernet connection, and then let my laptop serve as an SSH endpoint for that purpose. So as you can imagine, building a computer to do this with reasonable user responsiveness, I need to do some math, and I need to understand how the input-output requirements of this machine is going to work. So let's start with the output. From highest bandwidth to lowest bandwidth, we of course have video output. I need to be able to look at what I'm doing. Storage requirements will be on an SD card, and then the Ethernet adapter. You might think that Ethernet would be a high bandwidth peripheral, and in absolute terms it is. But when you consider how the Ethernet is going to be used, it will actually be a fairly low bandwidth device. So basically from an output perspective, each key that I push on a keyboard, or every time I move the mouse, it's sending notifications out to the out over the network, and it is not actually transferring bulk data. It's just tiny little messages. So that will be a fairly low bandwidth application. Input requirements, on the other hand, are a completely different matter. Because we're dealing with remote frame buffer protocol, the Ethernet adapter now is a significant bandwidth consumer on the input side because it's receiving video data from the remote server. The SD card and the keyboard and mouse, by comparison, are on the same order of magnitude as far as I/O capacity. So there are limitations to the Kestrel 3 as I had originally spec'd it, especially with respect to this application. The RAM is a significant bottleneck. It is a 16-bit path to what's called cell RAM. Has nothing to do with any other like memory technologies that Micron is producing right now. Basically, it's a pseudo SDRAM that I'm currently using in static RAM mode. So it is a dynamic RAM, but it exposes the pins of, say, a 62-256 SRAM, but with more address bits. It is a 16-bit path, and it has a 70 nanosecond access time. So if you do the math, it comes out to be about 28 megabytes per second throughput over that link maximum. 14 megahertz performance is a little bit odd clock for this FPGA board to calculate, so I'm going to drop it down to 12.5 megahertz. It happens to be 1/4 of the oscillator that comes standard on this board, and it's also 1/2 the VGA dot clock, approximately. It's about 0.1 megahertz slower, but it's perfectly adequate to generate a display. And so if we drive the CPU at that clock rate, we should get around 6.25 MIPS maximum possible performance, assuming we have no other load on the RAM. The reason I'm driving the CPU that slow, of course, is because if we drive it any higher, any faster than this, we won't gain any particular benefit. I should note, though, that despite this low speed, that 6.25 MIPS by today's standards is pathetic. Even most microcontrollers can put that to shame. But it's still actually twice as fast as an equivalently clocked 68,000 running on legacy hardware. So if we were to actually use this, it will, at this rate of speed, it will actually feel like a faster system, but it's actually not. In terms of video bandwidth, which as I had indicated earlier, at 640 by 480 pixels, with 8 bits per pixel, we're looking at about 18.5 megabytes per second. So remember, our original spec was 25 megabytes per second bottleneck on that RAM. Video is a monstrously voracious consumer of RAM bandwidth. So when you look at network, if you were to take 100 megabit per second Ethernet and you convert that to bytes per second, that comes out to be 12.5 megabytes per second throughput, but we only have approximately half of that available because of the needs for RAM. So we're going to be dropping frames at some point. So I'm kind of relying on TCP's flow control to help manage that a little bit. And then, of course, the CPU, which will not have a cache, and therefore it will really, really want to have full access to the bus as well. So after you take away the video bandwidth, the CPU and the network are going to basically duke it out with each other. CPU has the lowest priority in the system. It has to be that way, because otherwise you will never get anywhere with I/O. And when you amortize the amount of actual bandwidth left over after video refresh and expected network performance, the actual performance of the processor will probably boil down to 1.6 MIPS average, which is actually slightly slower than an 8 megahertz 68000. So in terms of usability and feel, I fully expect this to come in at just below an Atari 520 ST stock, something along those range. So if you remember the user interface, the GEM desktop of that era of machine, it will probably be about that slow. That's just my guess based on available math. It's plenty fast enough for keyboard and mouse management, but it's just barely usable. But honestly, since this was just a challenge for 5 days, I think I can live with that. Clearly, though, bit banging I/O is out of the question with a processor that slow. So I definitely need some kind of automated I/O system. And with that, I turn to channel-based I/O. Basically, a channel is a programmable DMA engine. And by programmable, I mean it has its own instruction set. The concept of a channel actually started with the IBM 709 mainframe way back in the day. But it was, I think, perfected with the IBM System 360. And I don't think I've ever seen a channel I/O architecture better than System 360 to this day. In fact, IBM's contemporary mainframes to this very day still execute unchanged the exact same instruction set as the System 360s did back in 1964.
And more of the size.
No, actually, it still sticks with the original set of 6 instructions. There are no changes to the I/O architecture from the software's perspective. Everything that is different is actually behind that interface. Like it's all hardware abstracted. Channel I/O has a certain characteristics, one of which is it's master-slave. Nothing goes through a channel without CPU intervention. Now, when I say CPU intervention, all the mainframers are going to be like, but stop, wait, you just said that this is supposed to alleviate the CPU. And that's correct. But the CPU does still have to say, here's a channel program, I want you to go and execute it. That's the extent of CPU intervention. But the CPU still has to kick off that program. So basically, the mainframe in particular, IBM systems, are always in the know of which I/O is going through the channel. It may not care what data is going through, but it always knows which channels are in use, who's using them, etc. As a result of this master-slave relationship, in order to have any kind of asynchronous I/O, the mainframe actually has to periodically poll that device. So if you've ever used a 3270 compatible terminal, you would type in your screen full of information, you'd hit the enter key, and there's a little light on the bottom of the screen, usually in a status bar, or it could be an LED. That light will illuminate for as long as the mainframe hasn't polled that device yet. And sometimes it'll appear as like a little clock down at the bottom of the status bar. When the mainframe actually polls your terminal, that light will go off and you'll get a new screen full of data. So it's fast, don't get me wrong, but it is still a polled I/O system.
Is it true that it grabs a whole screen full of data from you and returns a screen full of data? And it doesn't work on letters or sentences, it works on the entire screen.
So the question is, doesn't it work on full screens instead of individual letters? And the answer is correct. Yes, it is what's called a block mode terminal, because you use the same block I/O primitives as you would, say, a floppy disk or whatever. And that, by the way, is also the secret sauce behind IBM mainframe's ability to handle tens of thousands of terminals when DEC-VAX can only handle maybe a few hundred to a few thousand at most. Is because with the DEC-VAX, it is character oriented, and so it's got a lot more overhead. Whereas with IBM's mainframes, you just send the whole thing out as one big DMA stream, and there you go, it's all done. Channel programs, and this is, you heard me talk about the instruction set used by IBM's channel I/O. These are the entirety of the instructions. You have read and write for talking to individual I/O units. You have sense and control, which is basically read and write, but that addresses the controllers individually. And then you have transfer and channel, which is a conditional jump. Although they don't document it as a conditional jump, but trust me, it is actually conditional. For my needs, before I go on, I should say that with this simple instruction set, this works wonderfully well because IBM is in full control not only of this instruction set, but also of the software that uses it and the controller architecture that you attach to the mainframes, which means they can get by with a transparent byte channel that is strictly, I send you a message, I expect an acknowledgement back. And then you just keep going back and forth, back and forth. Unfortunately, with SPI, you don't have that luxury. SPI, first of all, exchanges data. You never send data and you never receive data. You basically exchange data. Now, I have instructions here to send and receive as an abstraction of that, but in terms of actual hardware, that's not actually how it works. Also, because it is a serial protocol with very few lines, you can implement SPI with as little as 4 wires. A lot of processes, a lot of handshaking is done after a certain amount of delay. So I need to introduce wait instructions as well. Then there's artifacts of protocols such as the SD and MMC protocol where you need to drop and ignore individual bytes. So I have a drop instruction, and so on and so forth. Like, I won't get into the full meaning of these. This is a topic for another talk entirely. But basically, I'm probably going to have around 12 instructions just to handle protocol needs for SPI devices. So let me give you an example of what a channel program would look like. So here's an SD card. Here's how you would read from an SD card. You'd basically send it 6 bytes, which contains the command byte, an address to read from, and an unused CRC. You would then wait for a response byte. After a certain number of clocks, you'll eventually get a data token byte, and then immediately thereafter, you have your set of 512 bytes. And then finally, you read and ignore the CRC because it's just not necessary overhead. This would be the command set for implementing that portion. Again, this is idealized commands. This is not representative of any real hardware yet. The idea is we send a buffer. It doesn't matter where the buffer exists in memory, but as long as we have the address for it and the length, then we have enough information that we can just blast. We can just stream that data out of the SPI. Then we're going to wait for something. What we're going to do is I'm going to keep sending FF bytes as per SD protocol needs. And then for every received byte, I'm going to logically AND it with FF, logically exclusive OR it with FE, and then I'm going to check to see that it's 0. If it's not 0, then I just keep doing it. I just keep waiting until that condition exists or until it times out. Assuming that we do meet that condition, we then start the read process. There's no, which during the read we keep sending FF bytes into this buffer for this many bytes. And then once we're done, we drop 2 bytes, again sending FFs as well. And this would all be done without CPU intervention. Now, the exclamation point here would be like a channel assembler flag that says, after the completion of the drop instruction, now you interrupt the CPU. Now you say, okay, we've successfully gotten a buffer. Now we can hand it off to the CPU to let the computer process it. And similarly with writes as well. So, because they do run independently of the CPU, I'm not bit banging anything, and therefore I can run this thing all the way up to the maximum oscillator speed on the Nexus 2, which for my purposes would be 50 megabits per second. SPI seems to be happy with speeds up to 104, 108 megabits per second. Beyond that, you start getting into clock skew issues. Now, for my needs, my earlier example there was kind of a high-level overview. I actually already have something of an I/O processor that I used as a tool to build and test the Kestrel 2 with, the S16X4 processor. Now, the S16X4 is a 16-bit CPU. It's certainly, as out of the box, it's not very adequate for this purpose because it only addresses 64 kilobytes of memory. But if I can make a derivative work of that, say widening that to a 64-bit address space, then I should be able to incorporate some of those commands as extended opcodes for the processor. So here, for example, is an instruction pack. The single hash would push a value, a 16-bit value on the stack, and then these double hashes here kind of work the same way as a transputer does, where every new chunk of data, you shift the top of stack and you OR in the new data. So by doing this with a single literal load and then 3 additional shift loads, that will give me enough, a way to load a 64-bit quantity onto the data stack. Then here I would load a length value, and then I would execute a send opcode that would actually commence the actual send operation. Now, because this would be an extended opcode, it would actually take up 2 instruction slots, one for the prefix opcode and then one for the actual opcode. That means that I don't have enough slots, so I fill in the remainder with the no op, and then here I would actually commit to sending to the wait instruction, which would involve the send byte and a AND mask, XOR mask, as indicated earlier. So this is just, again, this is all back of the envelope, but this is kind of what I'm looking at right now. Oh, and unlike IBM's channel processors, my channel processor would be Turing complete, which is advantageous in some respects, and it also has the disadvantage of introducing a security hole. So make sure that you keep this under lock and key. Don't let any arbitrary code run arbitrary channel I/O. But the S16X4 is proven. It is. I have demonstrated it in hardware numerous times. The existence of the Kestrel 2 itself is proof of that. So what is patient I/O, and why do I want patient I/O instead of just making everything master slave? So channel I/O is great if you have master-slave peripherals. You can't get any better than this. In fact, I would actually say that if you have the option of using channel I/O versus rapid I/O or patient I/O for such devices, by all means, use channel I/O because it'll just be faster and more efficient for you. But the problem is, I don't really have enough ports for like what I might want to do later on, like with optical, my project dot, my digital optical transmission, for example, which goes back to many years. But just the ability to add peripherals is very limited by this, by the available what's called PMOD ports. Digilent Nexus 2 only has 4 of them, and the AVNet board only has 2. So if you can imagine, by connecting the Digilent and the AVNet boards, I'm actually using 1 PMOD of each. So if I want to make extensions to them, I have to be very frugal with how I use my I/O. Here's a picture of what I mean. So here I'm using one cable for the SD card. Here I'm using this cable to connect to the AVNet board. There's the Ethernet port there. And then later on, you'll see that I also have plans for keyboard and mouse interface, which would probably use this port here. Now, it turns out that one of these PMOD ports is actually shared with something else on this board, which means that if I use up all 3 of these PMOD ports, I basically have exhausted my I/O on this. Well, except for this long connector here, but the mating connector for this is probably on the order of like $10, whereas this cable here is like $1, $2 at the most. And then, of course, I would have to fab a PC board and all that other stuff. Not fun. So to support 2 or more I/O devices, I originally looked at what IBM did, and they have block multiplexers and byte multiplexers that allows them to run multiple channel programs on a single physical channel. And it's kind of complicated, actually. In fact, when I tried, while IBM's historical documentation is fantastically detailed with respect to selector channels, which is your basic out-of-the-box channel, when it comes to block multiplexers or byte multiplexers and how they work and how the protocol works over the link and stuff like that, it is as opaque as a cinder block. You can't, there's like no information on that. So I decided to pass on that. So then I thought, okay, well, what about just making like a port extender thing? And the idea is the master would assert the slave select, and the first thing that it sends out is some kind of address. Once it receives the address, the port extender then asserts the appropriate slaves select for the address port, and then data communicates as you would expect. The problem with this is every device driver in the system has to be aware of these port extenders. So for example, if I come back here, you'll notice that I'm plugging directly into the motherboard, if you will. So the device driver for the AVNet and the device driver for the SD card, they assume that they're talking directly with the peripheral. If I run out of ports and I add an extender, all of my device drivers for both of these things would have to be modified, or at least go through some kind of indirection in the operating system to allow support for these port extenders. So it's actually very intrusive, and I'm not terribly happy with that. And finally, channel I/O is not a very good fit at all for autonomous peripherals. So for example, I'm going to use a keyboard as an example. If I hit a key on a keyboard today, what happens is a byte is transferred into a microcontroller in a PC. That microcontroller then sends an interrupt to the microprocessor. The microprocessor then reads from the queue in the controller, local controller. It then has to look this byte up to see if it's a printable character or not, and if it is, convert it to ASCII. If it's converted to ASCII, then and only then do you actually send it to your application. And there's a whole lot of other stuff, a lot of details that I glossed over. One of the major problems with the Kestrel 2 and its relatively poor code density was the keyboard driver. It just sucked up so much memory. It was just amazing. It took up easily 2 to 3 kilobytes of memory just because of table lookups. So with a packet-based system, what I can do is every time I hit a key on a keyboard, the keyboard itself can generate a transaction over the link, which under the, with the right hardware configuration will actually DMA that byte into a buffer. So half the logic of what goes into a keyboard driver would just disappear like that. And that's what Rapid I/O is. Rapid I/O is a packet switched I/O fabric that runs at a variety of speeds, but it's actually originally built for 1 gigabit per second or faster. It has 100% market domination in the 3G and over 75% domination in 4G cell networks. It basically has 100% market share in aeronautics now because NASA's selected Rapid I/O as the official I/O fabric for all new satellites going up. And when you think about it, it's actually a strict proper superset of everything that channel I/O does, because it's actually peer-to-peer, which I'll get to in a bit. Rapid I/O is also a set of openly available standards. You can actually go to this URL. You can download the PDF. It's about 1,100 or so pages, but you'll be amazed. I read through 1,100 pages cover to cover, pretty much without having any significant questions. It all made perfect sense. It was very logically designed, and like, I couldn't do better, and I tried. So when I was off at the Star Trek shoot today, one of the things that I wanted to do was, okay, well, 24 bytes of overhead, which I'll get to in a bit, seems like an awful lot of overhead, especially if I want to transmit, something small like a keyboard press or a mouse motion event. How can I do better? And doggone it, I couldn't do any better. Like, I really couldn't whittle it down. So the Rapid I/O is originally designed as a replacement for the PowerPC's frontside bus, and it's actually flexible enough that it can scale to something as simple as a 6502, or it could scale up to something like cache coherent NUMA machines. Rapid I/O is actually one of two preferred I/O fabrics for supercomputers for this reason. It also supports general purpose message passing. So for example, if I have a peripheral that would be substantially more convenient to just pass messages to instead of poking bytes in specific registers, we can do that. This is fully supported, and it operates on a first-class basis along with typical memory reads and writes. So I mentioned 24 bytes of overhead. This is where it all comes from. So each of these segments here is 1 byte. If for a wide segment here, for legibility reasons, I widen them out, but they're basically 2 bytes. So I have 2 bytes that comprise a start of packet indicator. We have a destination address. We have a source address. We have a byte that basically says I'm going to read, in this case, 8 bytes, up to 8 bytes. I have a transaction ID, and I'll explain that in just a bit. Then we communicate the address where we want to actually read from in the device's address space, and then we terminate with a CRC. Our next step is we wait for an acknowledgement. Now, this doesn't mean that the data is ready. All this basically says is, okay, I've received your packet. Now I'm going to forward it to the endpoint, or if it is the endpoint itself, I've received the packet and I'm working on it. Now, the transaction ID. I wish I had time to put this into the slide deck. Like I said, I finished this 15 minutes before the presentation. Typical computer architectures have a single microprocessor, a single bus, and then a number of peripherals. And what happens is that bus gets time shared between all these different peripherals, whether it be memory, whether it be I/O devices, etc. While that bus is in use, nothing else can use that bus. I think that's fairly obvious. So if you have 2 to 4 processors on a bus and a number of independent memory banks, for example, you can actually run into a situation where the more processors you add, thinking the faster you'll go, it actually slows things down, because what ends up happening is you get bus contention. So earlier in the 90s, we had these things called split transactions. Intel implemented them, PowerPC implemented them. What basically happens is it splits the address from the data bus. And the idea is your address bus gets routed to gets routed to basically like a crossbar switch. And what you basically transact your addressing completely independently from the actual data. So you'll actually be able to tell the bus arbiter, hey, I want to read from address 1024, but then you actually have to sit and wait for that data to actually show up because you could be blocking on an independent resource. But because the address bus is such a short duration burst, that will allow other processors in the system to be able to make similar requests. So you end up with something called bus pipelining, which is a very simple form of this, or you get full transactions. So that's what this transaction ID is. It's basically the best practice at the time where, okay, we've got a bunch of point-to-point links. There's no buses per se, but by knowing your destination, your source, and your transaction ID, this allows the switches to route traffic intelligently so that you can make use of available resources. Just to give you an idea, and to make math simple, if I have 10 banks of RAM and they're attached to 10 separate rapid IO ports, and I have 10 CPUs also attached to their own rapid IO ports, each of those CPUs can access a different RAM bank completely independently with no slowdown. So this will definitely allow you to scale up parallel systems very conveniently and with a very predictable performance load. That is where NUMA architecture comes in, and that's why Rapid I/O is one of two fabrics for supercomputing. To get back to our example though, we finally get our response back, and we end up with, again, the device will respond with a start a packet. We know our source and destination, or they're actually reversed here. I didn't do that, but instead of a read indicator, it'll have a response. This transaction ID will match the transaction ID that you sent out originally. So that allows you as the originator of the request to know which response goes with which request. And then followed by the bytes that you requested. And then packets terminate conveniently. Now, like I said, there's 24 bytes. I calculated this because in a traditional CPU, your address, your control, and your bus command all goes out one clock cycle, and then you get up to 8 bytes back in the subsequent cycle, very fast. Clearly, over a serial link, this is much more inefficient. So all this overhead with destinations and sources and transaction IDs and stuff like that, believe it or not, this is one of the reasons why Rapid I/O specifies using SerDes ports and various other extremely high performance serial ports, is because this entire packet, this entire frame will be sent in the exact same amount of time as a parallel bus single clock cycle, or approximately close to it. Because we're talking about buses that operate in hundreds of megahertz, whereas the SerDes ports were operating at 6 gigabits per second or somewhere close to that. So as I said, it is peer-to-peer. It is not master-slave, which means that my keyboard interface, assuming I use Rapid I/O, now has the power to know, okay, I'm going to stuff a byte into a memory location somewhere on some device. So a couple things. Number one, it cannot assume that it's stuffing bytes to a host microprocessor anymore. I could be typing directly into a disk buffer. Think about that. The last time a consumer computer could do such a thing was a Commodore 64. Believe it or not, you could actually tell the floppy disk drive to send bytes directly to a printer without any intervention over that 300 byte per second serial link. You could actually start this off, pull the cable from the Commodore 64, and it will actually continue printing from the disk to the printer. So this is the first time that this will be possible in a consumer grade computing environment. Each device has 34, 50, or 66-bit address space. So let me repeat that. Each individual device has up to 66 bits of virtual address. That's an awful lot of storage, especially when you consider you can have up to 4.2 billion devices per switch fabric. So you can imagine the storage capacity on this thing is just monumental, just phenomenally huge. Not that I will ever use it. Make no mistake about it. I'm actually, patient IO specifically says 256 devices and that's all you get. There's really no need for anything more than that. But you'll recall this 24 bytes of overhead seems like an awful lot for transmitting up to 8 bytes or so. And it is. It actually starts to make more sense though once you start getting to 32 to 64 bytes, which is what the original intention was. It was intended to be the front side bus for a cache controller. That's really where it comes down to. And since we can now operate over a serial link, instead of sending 64 bytes at a time, we can actually say, you know what, screw it. Let's make a cache line 256 bytes. This is 4 times more efficient than hypertransport. Hypertransport tops out at 64 bytes. And because it is a replacement for front side server bus, or front side bus, it is intended to be implemented entirely in hardware. Now, of course, I'm not implementing it entirely in hardware, at least not at first, but it's capable of doing it. The protocol is designed to support that. So patient IO is, besides a pun on the name Rapid IO, it is a mapping, if you will. It's an application of Rapid IO, which is a very generic IO framework, to something a little bit more specific. It is bound to SPI, Serial Peripheral Interconnect. Rapid IO's serial links actually use the same number of pins as SPI, but the reason I'm not using SPI, or the reason I'm not using Rapid IO Interconnect is because those PMOD ports, I want them to have the ability to work with legacy SPI peripherals, of which there are a ton of them. You have ADCs, you've got DACs, you have, like I said, SD and MMC cards. There are even network interfaces that use SPI. So I specifically want that. The other thing is SPI is natively supported in hardware and a lot of microcontrollers. So for example, if I wanted to build my keyboard interface that is a patient IO peripheral, I would probably use an Atmel microcontroller and just use either bit-banged or built-in SPI port for that purpose. And I want it to be able to work with this accordingly. So patient IO, besides being a pun on the name, is also truthful because unlike other Rapid IO technologies, this is intended to scale down, not up. So 50 kilobits per second is probably the slowest that you really want to go with this, but it's still fast enough to be usable. And I've measured the overhead. It's about the same as SD cards. So if you're familiar with how fast it takes to transmit data over an SD card interface, say a few tens of kilobits per second, it's going to be about that speed. It's actually not significantly different, maybe a few percentage points different. But remember that big fat connector that on the side of the Digilent Nexus 2? Well, that actually can support up to 400 megabytes per second per direction. That's about 6.4 gigabits per second per direction. And to do that, I would have to fill the open oscillator slot with a 100 megahertz clock. I would have to bond together 4 SPI ports, each of which are 4 bits wide and go double data rate. So all of this is possible, but it's interesting that patient IO as a spec is actually capable of scaling from kilobits all the way up to mainframe class IO capacities. Because your typical, just as a point of reference, one IO channel on a Z architecture machine today is about 10 gigabits per second. So it's coming close. So, like I said, patient IO attempts to pin a number of Rapid IO variables, because if you read the Rapid IO spec, you'll see a lot of things like, if you support this feature, then this bit field does this. If you support that feature, then this bit field does that. You know, a lot of conditional in the spec. Still pretty easy to understand, but still I want to narrow it down further. So 256 devices per fabric. That's my limit. Especially because we're operating over slower links, having the smaller addresses actually impacts overhead percentages quite significantly. And for the same reason, 34-bit address space per device. So if you have a device that does implement a 66-bit address space, you'll need to find a way to implement like a 34-bit window onto that space. All devices have a vendor ID of -1, which I'll get to in a bit. next slide, actually. And instead of relying on vendor ID for discovering what the device actually offers to the user, I rely on UUID-based service discovery. So if you're familiar with Microsoft's component object model, it works the same way. Basically, you query the peripheral itself and say, okay, what do you actually support? And where do you support it in your memory map? And then, of course, in order to make this like a halfway legitimate rapid I/O spec, I have to offer a number of what's called capability registers, or CARs, and then status registers like CSRs. So about that vendor ID. So rapid I/O, being an open spec, and having talked with a number of people in the rapid I/O community, they said, yeah, just go download the spec, implement it however you want, you know, it's all on you. It's great, awesome. The problem is, if you want to make a new device, you need a vendor ID in order to do that, because otherwise there's no way to bind a device driver to your device. The problem is, that costs $9,500 per year to keep and maintain that vendor ID. Way too expensive for a home brewer. Way, way, way too expensive. I could probably afford that because of my job, but I can guarantee you 90% of the people who read Slashdot, not so much. And not only that, but the vendor ID, like I said, like I'd mentioned, is actually an inefficient way of assigning bindings. So if anybody's ever looked at the source code to a Linux device driver that is for a PCI device, one of the things that you'll find at the top, usually at the top of the source file, is this huge, ginormous list of devices that are known to be compatible with this particular driver. And every time a device comes out that offers a register set that is known to be compatible with this driver, you have two options. You can either completely fake it in UDEV, or you can modify the source code to this driver. And it's usually just a one-line change, just to add that one registry entry in there that says, this vendor's, this model, and this assembly is compatible with this driver. And it's just a data structure. It's all data driven. It's actually very easy to understand. But the fact that you have to basically recompile a kernel module just to support a new device that shares a known binary interface seems ludicrous to me. So I decided to go distinctly against that. So patient I/O uses, like I said, a common-spired query interface approach. And it has the nice benefit that you don't need a vendor ID in order to support new devices this way, which means you don't need to actually pay anyone to maintain that. Not that I'm saying you shouldn't get one, but you don't need one. And that's the key. So that's what it looks like in C. This is what it would look like in fourth, since I'm in the fourth group. Let's say we want to hang up a modem device. Well, a modem needs a UART. So we know that we have to query the device to see if we have a UART. If it does, we slam the hang up. We slam the handset. Otherwise, we display an error. Fairly simple logic. So the way this works is we take our device ID, which we get from somewhere somehow, and we compare it against a 128-bit number. So in this case, whoops. So in this case, here's this ginormous figure. Now, in actuality, this number is going to basically be pseudo-random. You can use any UUID generator that you want, as long as it's consistent. And these IDs are, they define their own namespace, if you will. And so because these are such big numbers and they're pseudo-randomly generated and usually have an Ethernet ID influenced or biased into the calculation, the probability of a collision is basically on the order of millions of years, which means you don't need the central registry for all practical intents and purposes. And if you do find out that you do collide, you're instead of having a big, huge, long known compatible list like most drivers do today, you now have a very short known incompatible list. So basically, a device driver will check to see, oh, does this device, okay, it exposes this interface, but now, okay, now I check a vendor ID and I say, okay, yeah, no, it's not actually, I'm not actually compatible with this. But the probability of that ever happening, like I said, is on the order of millions of years, you know, for just one collision. So that's basically what it does. Also, when you query it, one of the things that it returns is a pointer to the particular register set that you have. And so here I'm, you know, doing the typical Hayes command set +++, wait 2 seconds, and then I would just send out the string for ATH, right? Very simple. At least at this level, very simple. So about that interface ID. So if you, now as a person who's making a peripheral, if you have this interface ID, then you're saying that I implement at least the required registers specified by whatever it is that interface specifies. That it implements at least the required control bits in what registers that you do support, and that you must be, that your registers are placed relative to each other according to what drivers for X expects. Now, the absolute location for your register block doesn't have to be at any prescribed location. It could float in the address space. But as long as your registers are relatively located against each other, then that's all you really need. In terms of interrupts, same thing. You have to implement the minimum complement that makes your X be X. And mailboxes and messaging protocols, remember I said that RapidIO supports generic messaging? Same idea here. If you support mailboxes, you have to support the ones that this device or that this interface implies, and it has to have a compatible protocol in order for your operational semantics to be backward compatible. So let me give you one example that I had brewing in my head is keyboard and mouse, because the Digilent Nexus 2 only has one PS2 port. That's all it has. So if I want to use both a mouse and a keyboard, I either need to buy an additional device that plugs into that last remaining open PMOD port, which is doable, certainly, and it's certainly very inexpensive. But the problem is now I'm talking a binary protocol that is neither SD, nor is it RapidIO, nor is it anything else that would be derived from these protocols. So I would end up with multiple stacks. So keyboard IO, mouse driver IO, and whatever else, you know, the network driver, et cetera. Each of these devices would have a completely separate networks or a completely separate device driver stack. So I can't leverage code that I have already written when I go to support a new device. So I don't want, and I don't want to continue using that particular IO model. It made sense in the Kestrel 2 because I didn't have a whole lot of memory space available, and you know, every time I loaded a new app, I always loaded in new device drivers. You know, it made sense there. But for a more general purpose machine, it's really kind of a hokey solution. Not only that, but let's see here. It was input only. So if you push the numlock key on the keyboard, for example, the state of your keyboard would change, but the LED wouldn't, because the computer would have no way to command the LED light to. With the queue in the hardware. Imagine if I also had to manage that in software as well. The CPU does have to pull periodically. For a keyboard interface, it's probably not a big deal, but for other things that you would expect interrupts for, that would be a horrendous thing. And like I said, this was the Kestrel 2's keyboard interface. So what I'm thinking of is I want to use one PMOD port for both keyboard and mouse. And this is the schematic. Each of these arrows here represents one of the PMOD interfaces. You'll notice that basically 3 of my 4 PMODs are used up. The 4th one I'm just going to leave open for now because I don't know if it'll interfere with other devices. So basically all my I/O is accounted for. You have an SD card, you have the network adapter, and then we have a keyboard and mouse controller, which would be a microcontroller. And that then talks the PS2 protocol to the keyboard and mouse. So this has some interesting characteristics. First of all, the keyboard interface is no longer memory mapped. Basically, we pass events around using message passing. So if you're familiar with graphical user interface programming and handling events, it's the same idea. Basically, you'll get like a little 8-byte packet that gets DMA'd into memory from somewhere, and once you enter, and that DMA engine will trigger an interrupt, that you then read that packet and respond accordingly to it. You isolate system firmware from keyboard hardware through generic scan codes. This is a big thing for me because eventually I want to support USB devices. I don't right now because USB is all big and scary for me and whatnot. I think I've had someone on Google Plus try to convince me semi-successfully that I should look at USB again, especially in light of this. But basically, this will allow me to abstract away the precise interconnect and just focus on the meat of what I want, which is scan codes and mouse position events. And the nice thing is the keyboard driver, the mouse driver, and the network driver will all share the same patient I/O layer above that, which will be very nice. So anticipated keyboard message. Messages include a length field to them. So basically, this is just a flat array of bytes. So if I type, I don't know, shift and then release the shift, that's something like 5 or 6 bytes in that one event. It can accumulate up to that many, and then it will blast this event. So the message length will tell me how many of these bytes are actually part of the message, and then I just inspect those bytes. Fairly straightforward. Mouse is a little bit more complicated. I have to send an 8-byte message for every event. So basically, this would support up to 8 mouse buttons, and then I would have 16-bit deltas for mouse motion. I don't know if I need 16 bits, but why not? I've got plenty of space left over. I could go 24 bits if I needed to. So the network adapter is something different altogether. This one's a little bit more sophisticated because of this. There's a bottleneck here. So the actual Ethernet traffic is occurring at 100 megabits per second. I can't change that. The line rate to the computer, though, is only 50 megabits per second. And similarly, I can't change that either, except to go slower, which I certainly don't want to do. So the strategy for this is to let the Nexus 2 board assemble an entire frame to transmit inside the FPGA, inside the memory space of the network controller's RAM first. Then I tell it to actually send that message by way of actual message pass. And the reverse is just the opposite. So the AVNet will send a doorbell, which is Rapid IO's version of a targeted interrupt. It'll send a doorbell to the Nexus 2 when it gets a packet, after which I then read the received frame at my leisure. So basically, no network traffic actually crosses that link unless unless the Kestrel requests it. So in that sense, it's very similar to channel I/O. But the fact that I can send a doorbell asynchronously is the missing key with channel I/O. So I don't have to sit there and I don't have to pull the network interface. Because if I have to pull the network interface, that will actually severely negatively impact performance way beyond the 50 megabit bottleneck. So basically, I'm going to end up using nRead and nWrite, and possibly even StreamWrite packets to access the network adapter's memory, and then use message packets to tell the network adapter what to do. Now, the interesting thing is that AVNet board that I showed you a picture of long ago, even though it's so small, that actually packs 64 megabytes of SD-RAM on that little board. That is 4 times the memory capacity of the Kestrel 2. There's no way in hell that I'm going to be using all that RAM for Ethernet traffic. So I could very easily use that for RAM disk as well. So if I were to make this as a patient I/O device, I would actually be able to have a UUID that says, okay, I'm a network adapter, but I'm also a RAM disk. And I can actually support both modes of operation by simply saying, you know, these are the features that I support. So that's kind of what I'm planning to implement right now. And everything so far has been built up around channel IO. So even the rapid IO protocol that sits on top has still been based on rapid IO, which means when a device wants to communicate with the host, to some extent, I still have to pull. Yes, I get an interrupt, but then I still have to read data, you know, I have to command data, you know, to send out and stuff. The problem, and this works great for SPI because it's slow enough that we can afford to do that. The problem is, what about that 6.4 gigabit per second link that I was telling you about? Eventually, you get to a point where with a 4 wide times 4 DDR SPI channel, simply loading the registers for channel IO will take more time than it actually takes to send the packet out directly. At that point, what you really want is a hardware bridge. Now, if you recall, rapid IO is intended to be implemented entirely in hardware. So what I'm doing is actually a hack. So implementing this in actual hardware is the end goal, if you will. I said once I have this in hardware and I have switches that work in hardware, then I will actually have an IO fabric that can operate at any arbitrary speed that I want. So the Altera DE1 could connect to the Nexus 2. The Nexus 2 could connect to the AVNet board, you know, and we can actually have parallel, you know, we can actually have a stack of DE1s sitting like an apple crate, if you will, in a Beowulf cluster, all connected with this patient IO bridge, and literally no need for Ethernet drivers or anything like that. The CPU on board 1 can talk to memory on board 10 with no CPU intervention whatsoever. It can do this because the bridge acts as a surrogate peripheral in the local address space. And you have these things called base address registers, which actually are kind of like segment registers, the old segment registers, that they define the start address, they define the size of the IO window, and they also say which device on the rapid IO framework or fabric that you want to address. And if you, well, I'm sorry?
Without benefit of a transaction with a central host or controller.
Correct, correct. Everything is kept local. And if you, how many people here, by show of hands, how many people here remember programming on the Commodore 64? You have these bits that you can control that says, okay, bank IO in here and turn ROM and RAM off over there. Yeah, so a couple people here, right? This is exactly the same thing, all grown up. Okay, so basically what the bar register, what the bar does is it says, at address X, for Y number of bytes, I want to talk to device Y. That is exactly the same thing as banked IO in the old 8-bit days, which means, if you recall the you know, some months ago when I first introduced the notion of the Kestrel 3 and how I came to its address space, not that I have any particular need to do this, but that actually means that the only IO interface that I need to be CPU accessible is the patient IO or rapid IO bridge. Everything else can actually be turned off, which means that I can actually have an honest to goodness 2 to the 64 bytes of memory if I wanted. Like I can bank all that IO out if I wanted to and actually address 4.2 gigabytes of memory. So now I think now you're starting to see why patient IO is like so appealing to supercomputer vendors and stuff like that. This is, and as I said, the bridge also acts as a local memory bus master as well for incoming traffic. And like I said, there's no need for the CPU to be involved, even to set up channel IO program for handling it. It is a significant hardware investment, though. It is on par with a CPU cache controller in terms of number of transistors, and that's because it is a CPU cache controller. Remember, front side bus replacement, right, for a PowerPC processor. So that was its very first application, was as a bridge to high-speed memory for high-performance computing purposes. So it's not a simple piece of hardware, but it is a tractable one. If I did implement it in hardware, though, it would completely eliminate 90% of the patient I/O driver software that I plan on writing. The only thing that you would really need is Fabric auto config, what they call enumeration, and to maintain a device registry. And even the device registry you can get rid of once you've configured it, but it's nice to have it handy for just being able to discover capabilities later on. So in summary, I'm using channel I/O as a means of recovering performance from an already addled CPU in this application. And it is serving as the foundation for later experimentation and development of rapid I/O compatible stuff. It also offers a consistent device model and a device driver architecture, which is something I touched on earlier. That means that I don't have to have like 16 network device driver stacks lying in memory just to support 16 individual devices. It scales from kilobits to gigabits per second. And switches, I didn't talk about switches in this talk, but like I said, it is a packet switched fabric. Switches offer zero overhead port expansion as distinct from the port expansion of plain vanilla SPI like I had shown earlier. The protocol is the complete protocol is actually fairly robust. There's a lot of different use cases. There's a lot of different nooks and crannies. But yet, after reading the spec, I'm fairly convinced that I could easily implement it in software. It's actually a fairly simple protocol. It's about on par. So if you were to make an SD card or an MMC card emulator, it's probably about as complicated as that, maybe even simpler. And second-gen hardware bridges is something that I plan on working on later on, possibly for a Kestrel 4. And that will eliminate pretty much all the overhead, like I said. That'll give me what I call breakneck or rubber burning performance. The idea of being able to push 400 megabytes per second on hardware that is consumer hackable is, I think, a nice opportunity for exploration and experimentation as to what we can do with that. So basically, I'm going to allocate channel I/O to drive the SD card, as well as for now, to serve as the foundation for patient I/O. I'm going to try to make the keyboard and mouse rely on patient I/O and use message passing for that. The network adapter has to be patient I/O in order to support RDMA, remote DMA functionality, and especially if I want to use it as a RAM disk. And then 2 device driver stacks, period. You have SD and MMC, and then you have patient I/O. Everything else should be expressible in those terms. And that basically means that the NIC, the keyboard, and the mouse drivers are just tiny little thin veneers on top of that. And with that, any questions? Wow, did I really flabbergast everyone? I'm sorry?
Your brain has been busy.
Yes, my brain has been busy. This is what happens when you work digital ingest at Star Trek New Voyages.
Yeah.
You basically, so let me explain the context here. Digital ingest is the most boring job on a film set when everything goes according to plan. Janitors have more activity to do than we do. The problem is when something goes wrong, because the footage that you're just dragging and dropping between drives, literally that's what we do. We drag and drop from one card to a hard drive. If something goes wrong during that process, or if a hard drive fails, we go from the most boring job in the world to the most valuable job by 6 figures. Because, no, I'm sorry, by 8 figures actually, because it costs, the footage that we capture is probably worth anywhere in the vicinity of $50 to $100 million when you account for all the vacation time, all the insurance for the buildings, all the property rentals, and all that stuff, right? So we're looking at significant investment. And if anything goes wrong, it's on me, and me personally, right? Thankfully, this last year, nothing went wrong, which means I had 2 weeks of time doing absolutely nothing but dragging and dropping icons on a desktop. So I had a lot of time on my hands to be able to read the Rapid IO spec, and keep in mind also that I had mentioned at the RISC-V convention that I presented at, the Rapid IO folks were kind of interested in what I was doing. I didn't at the time make the commitment to be able to use Rapid IO, but I said, I'm kind of interested. I asked the guy, I was like, how complicated is this to implement in hardware? And he's like, it's fairly simple. For him, it's fairly simple because he's got all these libraries that he can rely on. He's like, yeah, you can just download the spec, implement the spec however you want. We're not going to stop you. I mean, just be aware that you can't use the Rapid IO name because you're not paying, the Rapid IO Trade Association for that right. And, but yeah, you can do whatever you want with it. Cool. Okay. So I've made the announcement some months, like back when I was at the movie shoot, that I'm really looking into using Rapid IO. This looks really interesting. And then all of a sudden, Rapid IO Trade Association follows me on Google+. And now they're following me on Twitter. So to the best of my knowledge, I am literally the only consumer grade product that is available. Well, it's not available yet. Will be available for under $200. Yes, it is conceptually available for less than $200.
So the question is, what's your development time to some alpha state prototype?
Development.
Money you got?
Yeah. How much money? How much money do you have to replace Rackspace as my source of income? So right now, my employment with Rackspace is obviously taking priority, and we're in a crunch right now. So obviously, I don't have a whole lot of time locally. But that said, I am in the process. I want to get to a point where I have a semi-usable Forth environment working. I do have RetroForth installed on it, but it's still, like I'm not comfortable enough with RetroForth to be able to say, okay, I can use it fluently, right? I want a system that I can use fluently, that I can access hardware resources on, that I can actually develop on the system. I just implemented SD card emulation in the Kestrel 3 emulator. Now, this is a big step. This is a major enabler. What's that? I've been working on this for a long time. Yeah. Yes. There is no relation, but I have heard people babbling about making a Wishbone to Rapid IO bridge at the RISC-V conference, but I don't know of any projects definitively yet. Yeah, so Wishbone is a parallel wide bus. And because of that, if I wanted to make a 64-bit wide bus, I would basically be consuming 128 routing resources minimum inside the FPGA. Now, on an FPGA like a Xilinx 3, SC1200, go for it. You've got plenty of resources there. But on a smaller FPGA, you'll run out of routing resources. I'm sorry? But you still have routing resources inside the chip. You have to connect logic blocks to logic blocks. And those are the routing resources that I'm talking about. The nice thing about Patient IO is it's not designed so much for on-chip interconnects, but it's chip to chip, which means that it's optimized for a small number of pins. Right. SPI is a bit of an extreme example. Also, the 1-bit lanes for Rapid IO is an extreme example. The nice thing about Rapid IO serial links is that they're spec'd using SerDes, commercially off-the-shelf SerDes. So you're looking at anywhere between 1.25 to 6.5 gigabits per second on these links. So you can afford serialization on that and actually still be able to pull off, you know, hundreds of megahertz equivalent performance. When that's not possible, though, they also define a two wide, 4 wide, 8 wide serial interface. Then from there, they also have a parallel interface, which is still kind of semi-serial, and a 16-bit wide interface as well. So worst case, you would probably be using close to about 80 pins maximum, which is still a lot of pins, but when you're talking about, you know, 60 to 120 gigabits per second equivalent throughput, you know, a Euro card, for example, has support for 96 pins. So you've got, you know, that I think was their motivating limitation. But for use on chip, you definitely want to use Wishbone. For anything else off chip.
So it actually sounds to me, it's almost like a DMA, but reverse. Let's say you have a DMA controller to the processor, the device you're talking to is off the rack.
Yeah, so it's a replacement for a front side bus that is busmaster capable. So exactly. So it's completely peer-to-peer. Yep. Yes.
Since we're at the end of the break now,
Oh, sorry.
we're going to thank our speaker again, and there'll be a short lull in the action. And what do you think, John?
Yes, let me get it up there. I'm going to move Sam out of the way.
Okay. So the will start up again in a little while. TBD.
Okay, so
Currently less than or equal to 15 minutes.
so for people who are watching, we're going to take a short break. Duration is unannounced at this time because I accidentally overflown into our scheduled break time.
It wasn't an accident.
Yeah, you're right.
It may not have been your purpose, but it was mine.
So yeah, just wanted to let you guys know I'm going to turn off the mic now, and when our speaker comes back, or when he's ready, rather, just remember
Hello, everybody. My name is John Harbold. Thank you. Okay, that's it. Last time we were here, you remember metal gearbox holding a 150 gigabyte POTA drive from yesteryear. And I had two versions of Fedora Linux, a 32-bit and a 64-bit.
If you could unplug it from the wall plug and stand right where your name is on the projector, folks at home.
Whoops, I didn't want to unplug that guy. Okay, that one.
Or I could have moved the camera. No, this is more fun.
Yeah. This guy right here. 150 gigabyte
A little lower.
hard drive inside.
Really?
Yes, 150 gigabyte. Just remember, okay, last time I was here, I had two versions of Linux on here, a 32-bit and a 64-bit. And that was just to see if I could actually do it. Well, this time, I now have three. The same thing, I have a 32 and 64-bit Fedora 22 Linux and the latest Ubuntu 64-bit on here. So, and here's the other thing. These are not live installations. These are full installations. Just like if you had installed it on your hard drive, on your laptop or whatever. Okay, which means it acts just the same way. You can run with it, and you can also update it, which means you can update new kernels, and you can add and subtract applications to your whatever you want to do. Okay, and the nice thing about this is there are times, you know, when you have a computer that might croak for some reason. It won't boot. Well, if you could plug in one of these guys and use the BIOS to boot from the USB disk, you might be able to rescue your system. Something might be wrong. You might be able to have to go in and repair a hard disk. That's the nice thing about Linux. It supports many, many file systems. Not only the ext versions, but it does do NTFS, all the FAT, even what's that company down in off the 280? Oh, Apple, that's right. That file system. Yeah, So, and also the nice thing about it is, if you have an old computer, say a 32-bit Intel, this will boot off of it. Most of the processors, most of the computers now run 64-bit. And also, USB is pretty pervasive on systems. So that's why I chose USB. Also, the nice thing about developing with Linux is there are partitioning utilities. So you can break up a disk into several partitions. And most things like with Linux, you can get live and network installation CDs or DVDs to be able to install onto your system. So, you know, especially like I said with Fedora and Ubuntu. Okay, and the basic thing, the most important thing that you want to do here is you have to be able to partition your disk. Now, the disk I just showed you has 150 gigabytes, so I just basically chopped it up into somewhat like 50 gigabyte chunks so I could have three different installations. The one I used, the partitioning one, is I used gparted. It's a graphical partitioning program. First thing you do is you just pick up a disk, delete all the partitions. Okay. Then for that whole disk, you create an extended partition that covers the whole disk, because that's important. If you use extended partition, then you can put as many other partitions inside it. The last time I was here, that disk I didn't have extended. I just used primary. only problem is you can only have 4 primary partitions, and I used them all up. But I just want to do it as a proof of concept. Yes, Dave?
Isn't a primary partition, unprimary partition necessary?
No. This one I have here is one extended. Now, you might need a primary partition if you want to install Windows.
Yes, that's not thinking.
Right, but exactly. Windows is for wimps, as far as I'm concerned. If you're truly a manly programmer, you will run Linux. Okay? And if you want, literally, you can have a metallurgical assay of my computational testicles. You'll find that they are solid brass. Yeah. Okay, enough of that. What you do next after you've created the extended partition is, what I did here was I created a 64-bit partition. That should be not wrong. This is not the primary partition. This is the extended partition. And this will be called SDB, well, 1. And because this is a full installation, I need a swap device, just in case, for some reason, I need to run many programs at once, and I don't have enough memory in my computer at that time. This will allow you to save them off on the disk. Okay, and then, okay, this is wrong. This should actually be 32-bit. Okay, create that. Now you do the same thing. You also create a swap partition, save it, and exit. Now, this is the steps. This is G-parted. As you can see, well, all right, 149.05 gigabytes. I deleted all the partitions in there. Okay. Next. There should be, let me go through some more of these things. God damn it, son of a bitch. Excuse my French. Okay, you see this? This is one of the things I don't like. This guy says it's there. If I come over here, as you can see, it's not there. And let me see if I can insert that guy. Okay, well, right now we're SOL. Okay. Huh? Where is the image? Yes, that's what I want to know. No, it was there before. I just don't understand what happens. But you will see that what you want to do is you want to create, in this case, a 64-bit partition. Okay, in this case it's, well, I wish I had the image. Crap. What you want to do here is create the partition. In this case, since I have 2 gigabytes of memory on my laptop, I just made the swap file 4 gigabytes. So let's see if I'm not right. Well, let me go down to actually the end here. God, why did this happen? Okay, hold on. Let's pray that I can restart this thing. Okay.
There we go.
Oh, there we go. Okay, let's start over again. Okay, let's page down. Here's what it looks like when it's empty. The next thing you do is you create a new partition. And no, this is creating the extended partition. You can see this is the whole guy there. The next one is I create a partition for a 64-bit guy. And in this case, you can see this is how big it is, and this is how much free space I have. Following that, I want a swap file. And this is the swap file right here. And you can see it's only 4 megabytes. Then following that, you create one for a 32-bit Linux partition. Okay. And you do the same thing there as you create a swap file for it. Then, this one,
64-bit Fedora.
okay, that's all right. Excuse the little problem there. I can always change that, edit that out. But this, we're creating a 64-bit Ubuntu partition, which will be the remainder of what's there. And it's a swap file. And this is what the whole thing should look like, right here. This is the 64-bit partition. That's its swap file. This is the 32-bit partition. This is its swap file. This is the Ubuntu 64-bit and its swap file. Yes?
Why do you have a separate swap file for each one?
Well, there is a reason. I just want to make sure that they all are separate at that time. You're right. I could have one swap file shared among these guys, except what I'm going to do next month. And that is using virtualization. Right, where all of a sudden now I can have all 3 of these things running at the same time. Okay. And this shows the layout. Okay. And then what you do here is you say save, and that will partition the guy. Now, you want to do installation. Basically, I assume you guys have installed software before, right? In this case, you can go to Ubuntu. You can get a DVD installation, ISO, burn it on a DVD, stick it into your computer along with the USB disk, reboot your computer, and oh, here's the thing. The BIOS should be able to detect if it has a USB port, a USB disk already plugged into it. And you want to be able to select that guy. Well, actually, excuse me. You don't want to do that. You don't want to boot off the hard disk. You want to boot off the DVD. Okay, once that happens, then you just follow the instructions for doing the installation. Yes?
Does Ubuntu no longer fit on a CD?
It's on a DVD now. That's the one I used was Vivid for Vet.
Wow.
Yeah.
You can get a base Ubuntu system to fit on the CD. You just won't have any development.
Right, exactly. I just wanted to get this thing in. And once that happens, then you'll have a bootable partition that's running 64-bit Ubuntu.
You can tell it to install it on the
Yes, because what it'll come up is say, where do you want to put it? And you just say, okay, here's the partition I want to go on.
those partitions will have names like D, E, and F. and stuff.
Well, okay. What they have here, let me go back. Okay, see the drive names here?
Yeah.
Okay, in Linux land, it'll be /dev/sd, in this case, B, because usually SDA is your internal hard drive. Okay, so,
Okay, got it.
yeah. So you can see here, this will be SDB1, SDB2, 3, 4, 5, and 6. And again, this is installing the Ubuntu. Fedora, the nice thing about Fedora is they support network installation. So you really don't need to install from a DVD. You just, and I assume everybody here has got an internet access. And it's just the same thing. Yes. Just put the network and installation CD in your drive, boot from it, follow the instructions and say, okay, this is where I want to put Linux on these partitions. And let's see, am I done? Oh, here's the other thing. Because this is a live installation, I mean, these are a full installation, you can update them. Because one of the things you'll find with Linux is you'll get constant updates, bug fixes, security fixes, you know, for the kernel, for many of your applications that you want. So what you want to do is you boot your particular partition, open up a terminal window, log in as root, that's what the SU dash means, and then you say DNF update. And it'll go out and check to see, oh, is there anything newer out there in the repositories? And then it'll make sure it downloads, updates, and now you'll have you'll have an updated system. That also includes kernels. Also, if you want, you can install applications. And this is one of my favorite applications here. And that will go out and check to see, oh, we have that program, I want to install it onto the system. The last thing you want to do before you reboot is you want to reinstall grub2. Because one of the things the installation will do is it'll do what's called an OS probe. And it'll check to see if there have been, if something new has been installed for that partition. All right? So that's basically it. So what I'd like to do now is, let's see, I'd like to actually show that I've got this stuff. I'm going to reboot. Okay. Oh, crap. Well, that's because I didn't turn it on. Sorry, guys. Okay. What? Yeah. Yes, I know I'm connected. Just if I didn't have my head up my ass.
Warning, system under test must be connected or it will refuse to function.
That also includes the okay. One more time. There we go. Whoa. What the? Does this thing have power?
Switched on.
Yeah, it's switched on. Yeah, plugged in both ends. Here, here, here. Okay. Let's try this one more time. I don't want to look like such a putz. Okay. I heard something. Oh, crap. Well, let me try this thing for 1 second. That might be something, well.
That blue light.
I got a blue light, good.
It's a blue, yeah.
Okay, give it some time. Yes, that is Fedora booting. But it's booting off of the internal hard drive here. Yes, yes, yes. Yeah, it did. It said, what USB hard disk? Who do you think you are? Yeah, I mean, and you're using a PATA disk? Get up with the times. Okay.
Parallel ATA.
Yes. Come on. Do I still have a blue light here?
Yes.
Good. Okay. Okay, let us restart. Restart. There we go. Well, you can't see it, but it is up here. Do you believe me? Or you think I'm funning you?
We'll see.
We'll see. Okay, I'm going to go down and select USB hard drive. Okay, here we go. Now. Oh, you can't see it here. Huh?
Select you want.
Okay, here, that's what I'm going to do. Is there any way I can get a picture of this so you can actually see the? No, okay. No. Okay. I've got I use Grub 2, and it shows that I've got. Yes. Can you zoom in there? Well, let's just say that it won't show up on the BIOS, but can you get a shot of it? It can actually show the different sizes. I've got Fedora 64-bit. I've got.
I doubt the people at home can actually
Okay. Nah? Can't do it? Okay. Yes, I've got 3 versions of the 64-bit kernel, 3 of the 32-bit, and I've got Ubuntu. And I will select Ubuntu. In fact, I'm going to select the advanced options for Ubuntu. And I'm going to be selecting a 3.19.0-25 generic. Generic. Come on, get in there. What is this? There we go. Okay, Ubuntu is now booting up right now. I just wish it was. Oh, there we go. Right. And you guys thought I was pulling your leg.
We had no doubts.
Okay. And that's coming off this metal gearbox. You know, Ubuntu's okay, but Ubuntu is several versions behind. It's like Red Hat, Enterprise Linux, and CentOS. They're okay, but they're several versions behind. That's why I like Fedora 22. Well, I like Fedora, bleeding edge Linux. Okay, now, okay, that's really interesting. You can't see what I see, so you can see, oh, there we go. There we go. Okay, where I'm logging in. And Kevin, you can verify that the blue light is blinking away. Okay, here we go. That's right. Okay. Let's see. Ubuntu Software Center. There we go. Oh, that's right. I want to go out on the net.
Which USB 2 or 3?
2. This is, yeah, remember, this metal gearbox I bought several years ago.
That's what it feels like.
Yes, yes. I'm not here for a thing now. I do have a little problem with my network.
Well, you did log in.
Come on. Okay. I'll just do Stanford visit. And you can download stuff, right?
Yeah. Fine.
There we go. Loading up. Oh.
And now you'll need your browser.
Okay, now a browser. Let's see. Firefox. Now this is visitor now. So this thing will not ask for a password.
It will ask for an accept.
Did I click on that? Yes, I did. It is a bit slow, as you can tell. This is a USB 2.0. Both ends. My laptop is from 2008. It has two, count them, two 64-bit processors. I can see you guys are impressed. Let's see. Come on. Because I do want to show that, yes, I can get software off the net. But this thing.
Browser. Click again on it. Oh, they're down there at the bottom. No, they're not.
Oh, notice here. These are the other partitions. 32-bit, 64-bit. And also my laptops guy is in there. Okay, maybe if I... Excuse me? I don't want to.
It's called PSOD. Yeah.
Oh, here we go.
There you go. Oh.
Okay, what is this page? I don't care. Okay, what happened? Dave, am I supposed to get something?
I don't know. I'm not a Stanford visitor, so I never use that.
Okay, that's all fine. That's fine. Let's come back up here. Let's go click. Let's.
No, not Stanford Secure, that would be bad.
More network, there, yeah.
You disconnect from disconnect from Stanford Visitor first. Okay.
And now Stanford.
Now you try refreshing.
No, not those. Not those. Not those.
Try refreshing in web page.
ShareBot.
ShareBot? What? Oh, here's Stanford.
You're in Stanford, you're fine.
No, he didn't log into Stanford. He was in Stanford Visitor.
Yeah.
Disconnected from that. And now he wants to. Now
What's
you
wrong?
need to go to a web page and log in.
Stanford, let me refresh
Oh,
this.
wait a minute. Oh. Yeah, you're trying, it's trying to do the web auth at Stanford. And Firefox is saying, yeah.
That is gauche.
Yeah,
Okay, well,
Firefox doesn't like doing this.
okay, all right. Well, no problem. We can go and say, all right, enough with Ubuntu.
Does it go down that far?
Yeah, I'm gonna say enough with Ubuntu. If it's not gonna let me get on for whatever reason, I'm gonna get on with a Linux version I know works.
For the record, I have to log on. Do you use Firefox? Yeah, in fact, I use Firefox.
Okay, gonna reboot off the USB hard drive. And this time, I'm going to use a 64-bit Fedora 22. And
Close enough to be able to talk to that.
you mean out the port, like it's supposed to, should be real quickly. Yeah, all right. There. Fedora 22 is now booting.
From the lower left to the upper right.
Yes. And if you're real quiet, you can hear the hard disk.
Oh, we can see it.
Yes, it's flashing. I can hear it. You know. That's funny. In the future, that sound isn't going to happen anymore. So everything's all going to be solid state. Huh? You think rotating media is going to be around?
Yeah, it's gonna hold for a little bit longer for a while. It's still, maintain the silicon.
Yeah, not yeah, that isn't around anymore. Okay, no. Okay, I'm surprised at that. Okay, I'm going to log in and hopefully they'll. Are we seeing? Oh, good. We're seeing stuff. Okay, hold on. Let me configure the display. Mirror. Can we see stuff?
Yes.
Okay, good. All righty. Let's see if this Fedora will work. Okay, server FM. Sanford. Okay, we're connecting. You can see you got there. Oh. Oh, I got an IP address. Security. Dave, none?
None.
Identity. Okay, automatic deed.
Automatically, yeah.
Okay,
Oh, it canceled.
why? Don't.
What is Stanford again? Apply.
Okay.
Now, dismiss that and just hit
Looks like you're connected.
There we go.
All right, so tell it you want registration choices. Now tell it you want wireless guests. Now tell it you want guest network access. Now tell it you want your SVFIG. Capital A, yeah, there you go.
All right.
Dash.
Huh?
okay.
Let's see.
August with a capital
AUGUST dash FIRST. Yeah, capital F. Did it.
There you go, you're on.
Okay. That's okay. Like I said, this is. Well, actually, what I'm going to do is this. Bring up a terminal. See, I'm old school, guys. Log in as root. Up yours. Okay, I want to do an update here. Since I have network connectivity. It's been a while since I've done this, at least 2 weeks. So you can see we're going through the motions right here. There we go. 480. Oh, boy, look at my rate drop. Oh, look at that. Am I taking too much bandwidth right now? Or is someone watching porn? Don't give me that. You're the guy watching the porn. You're all the way back, Sam. Since I'm a private person, I don't want to know. Okay, nevertheless. Okay. There we go. Let's go and look at. Okay, let's see what's happening with Fedora. Oh, here we go. Look at this. Look at all that. It got updated. New kernels. Look at that. So I can say yes.
Now it starts. You are gonna make that.
Wow, you're right. Look at that. Look at this. No, that's the nice thing about this. When you do the update here, it won't crash. If you're in the middle and something goes, it'll just say, oh, well, you were in the middle of something. Oh, wow. You can see I'm over here.
0.
Yeah, you haven't even hit the 1% yet.
Yeah.
So what else are you gonna show us? Just
Not that I care, but yeah, just so you can see, you now, in this case, I'm updating a 64-bit partition. Anybody have any real old computers they like to see get rescued or anything like that? I don't think I can do it. No, in fact, I might walk off with that Altair.
Yeah, I wouldn't plug that in until you check the capacitors.
Well, you know what? This is going to take a while. I think I don't really care to show that. So I'm going to give it the hand of God. Control C. And let's see. Oh. Oh, I don't have it. Oh, Lord. Yeah, maybe I can do that. Let's see if that will install. APPER, it's a...
No, it's effort, A-P-P-E-R-T.
Ouch.
What does APPER do?
Application installation.
That is data expiration.
Whoa.
That is a concept.
Look at that. Wow. Forget that. Yeah, but this is the nice thing about DNF. You notice I said, I want to install APPR. And it goes, oh, guess what?
You have a bunch of other ones.
Other things, dependencies.
Oh, dependencies, yes.
Right. So I'm just going to say no.
Well, it's 66 megabytes.
Yeah, but
That shouldn't take more than half an hour.
yeah, then we only have 17 minutes, if that. So as you can see, I booted 2 different OSs. Okay, so this is nice. My next trick will be to be able to boot virtually. Yes, and one of the nice things, excuse me, see this? Fedora workstation, that's what I've got running on my laptop. It also has a server, but it also has a cloud so that you can run virtual. What it does is it installs a really tiny Linux on there, just enough to get it going so you can, and it uses something called Docker, which is ability to install virtual things. And my next trick will be to try that. Now, it might be a problem because my metal gear box here is a USB 2.0, and that runs real slow. Even though the clock speed's 480 megahertz, it ain't nowhere near USB 3.0, which is 5.1 gigabits per second, versus USB 3.1, which is 10 gigabits per second. I just might do it as an exercise because I've got a whole lot of other hard disks. I just want to try it out just as a exercise. Yes?
You have USB 3 on your laptop?
USB 3 did not exist when this laptop came into existence.
Buy a new laptop next time.
Oh, okay.
Yeah. You know this computer that I'm watching porn on?
Yeah?
That's USB 3 on it.
Oh, really? Well, and you think you're better than me just because you're watching porn?
Just young.
Yes. So, okay, let's search for.
Get your revenge. His name is on the Ashley Madison list.
Okay.
We probably need to clean up a little bit. Actually.
Whoops. Let's see. Here we go. This is the one. Project Atomic. You can create and run applications in Linux containers, which means they will all run at the same time. Not that I want to try to do more than 2 on this thing, because I only have 2 processors. But this is nice. This is what, and also a nice thing, you should be able to install Windows.
Windows 10, and it hasn't hit yet. I've just been going through a bunch of stuff with Docker and Kitematic. They didn't handle Windows 10 properly. Actually, it was Oracle's VMbox. VirtualBox.
All right.
Did not handle Windows 10 properly, and so they had to update, and that was a whole nightmare they had.
So if you try to do like Windows 8 or Windows 7.
Perfectly fine.
Okay.
It was the Windows 10 that Oracle needed to update VirtualBox.
I may try that. I may try it.
Now it's running Windows 10. But I have not seen the Windows 10 container yet.
All right.
I have it
Soon.
supposedly coming.
Yeah. Yes.
What about having a Linux kernel with the KVM module built in so you run both Linux and simultaneously from your hard drive?
Yes, that's what this this guy right here. Cloud. Well, that's the whole idea about cloud. It runs things, because here's the thing. If you look up here at the top, it says create and run applications in Linux containers. Linux containers will run virtual.
Right, that's awesome.
As well as local, right?
Local?
Do that locally. Docker effectively is running multiple Linuxes with each container right on your local system.
So Docker, so when you're talking internet, Docker is a logical container. It's not an actual virtual instance. So it's the same kernel, but it's just configured so that the kernel has tighter control over processes, which parts it's using, how much RAM it's in, etc. But it is the same kernel. LXC, Zen, KVM, these are all virtualization. They're true hypervisors.
So it's Docker more like a true SVFIG.
Yes. Yeah. It's not that big.
The other
Organization about running different ones on different boards.
No, Sam knows more about lower than I do.
Well, that's the company I work for, does a lot of organization. We invented OpenStack now, between me and NASA. So, and our stuff runs Zen KVM for stuff. And then nowadays we're starting to incorporate Docker as well.
So Dave, would you like the slides after I've edited them?
Yes, please.
And who do I send them to?
You can send them to me.
Okay.
Send them on to Dave.
Okay. So, yeah, because I do have to edit some of the boo-boos in there. So, yes, this is something because one of the things I'd like to do is be able to get back to porting GeForce to ECOS. As you remember, several years ago, I was close to doing it, but I didn't. I ran into problems because my computer died. But I still have the hard disk. And once I get that all squared away, then I should be able to run virtual.
Okay, hand him the microphone. He's got just a quick announcement.
Okay. Handing off now.
Are we all turned on here?
We're all turned on.
All I have to do is, I'll just hold it out and leave me here for a minute. Oh, you want to be able to see me? Oh, they don't hear if I hold it? I heard you the first time. That sounds strange, but I'll take your word for it. You've used it and I haven't. Okay, my name is Glenn Worstel. I'm presenting next month on MeCrisp 4th, and this 5 minutes here or less is to tell you what you want to do if you want to prepare for this presentation. So what to do, and I'm going to put this online here in a few days anyway, but if you want to get a head start, Google on MeCrisp and you'll find a place to download it, and then you can download the whole thing. It's not all that big, and it includes code that will run on a whole slew, 15 or more, of cheap development hardware boards that you can get for anywhere from $10 to $20. And I have it running on at least a dozen of these just for fun. And you can also run it in a simulator. And by the way, this thing runs versions of that run on MSP 430, Cortex M0, M3, and M4, different versions. And the instructions in the README tell you how to do it for all of them except the very cheapest one, that's one from Chinese. And I'll put the instructions online for that. And it's a pretty well done, actually I think it's very well done. The guy's brilliant. What else can I say? If you want to get a head start, download it, read the README, read all the different macros it'll run on. Go buy one if you want, or run it in the simulator to try it out. So if there aren't any questions, that's it.
We're done for today. See you all later next month.